So, dear colleagues, I think now it's time to start our seminar after summer vacation. And today we have a guest from Düsseldorf University, Dr. Guido Reiss. Dr. Guido Reiss studied chemistry at the University of Saarland, and in 1992 he moved to the Technical University Kaiserslautern and defended in 1996 his PhD thesis concerning the precipitation of some rhodium complexes for the recycling of catalysts using in car. The diploma thesis and PhD thesis work were both closely related to the crystal structure determination. And since 2003, Guido Reiss works as a senior researcher belonging to the permanent staff at chemistry department of the University of Düsseldorf. Besides the task in teaching, his main interest is focused on the synthesis and characterization of new polyiodides. In the field of crystallography, he deals with pseudosymmetry problems to elucidate the true structure of compounds. By now, Guido Reiss published about 200 articles. From 2006 to 2019, he was a member of Senate of University of Düsseldorf, and from 2009 to 2011 as vice president of the Senate. And I would like to say that in August of 2024, this year, he visited Ukraine, and also he visited Kharkiv. And this, in my opinion, proved that this person is very brave as our city, Kharkiv. And dear Guido, please, you can start your lecture for our participants.
Yes, thanks a lot, Valentin, for this kind introduction. And I was really happy to meet you all in the Institute. So today, I want to show some results from our research concerning polyiodides and iodine-inclusion compounds. We use some special tools from crystal engineering, and I will, yes, present some of these results. My schedule for the day will start with a small history of polyiodides, then some applications. I want to present some methods we normally use. Then I will, at the end or at the main part, show our systems, our template systems we use to create special polyiodides. And as a last chapter, I will show some iodine-inclusion compounds. Okay, let's start. The historical background goes really back to 1812 about, when Mr. Pierre-Joseph Pelletier just found an interesting reaction. He reacted iodine with strychnine and got some orange or red products. This is more or less the first appearance that we just see in chemistry, a polyiodide, and nowadays we know that it is the I3- ion he just produced. Perhaps you know him from his work on chinin, together also with Mr. Caventou. So polyiodides are compounds that are created by the reaction of a iodine molecule with the I-, then we get simply the I3. You see it here, just combining iodide with iodine gives the I3-. Then we can combine two anions with one molecule, we get the I4-2-, and so on. In this case, we have one anion and two molecules. These dashed lines are just halogen bonds, as you expected, and but there is still a big question how to synthesize topologically specific polyhalogenides. So just how we can get a special type, a special topology or something like this. In general, the halogenides and the polyhalogenides are, yes, investigated for many decades. For the polyiodides, several groups just filled up the gaps here. We just were at 3 steps active and filled the gaps. So this work is more or less done. For bromine, there is still some work to do. And for chlorine or even for fluorine, there is not a lot published so far. The bonding in polyiodides is understood as halogen bonding, and one name should be highlighted really strongly. It's the name of Peter Politzer. Peter Politzer just understands halogen bonding as I just cited here that a halogen bond is a sigma hole bond, and a sigma hole bond is a non-covalent interaction between a covalently bonded atom of group 4 to 6 and a negative site. To make it more handy, we have here a molecule with a iodine. This is ICF3 molecule, and it produces here the sigma hole. A sigma hole is simply a part of the molecule which is not so electronegative, and this interacts somehow with this lone pairs of a water molecule, and this is this sigma hole bond all people discuss. So polyiodides have a lot of applications. First of all, we know that polyiodides are just used in lithium batteries. They are used in zinc iodine batteries. They are nowadays also used in some polysulfide, polyiodide batteries. This is this part of battery application. Then you know some cheap solar cells, the so-called Grätzel cells, more or less named by Michael Grätzel from Switzerland. In these dye-sensitized solar cells, the polyiodide system is this electrolytic system which transports the charges. And we also see some new papers even on perovskites, and perhaps all of you have already have contact with, contact with a polyiodide, and it's because it's used as a wound disinfection agent. And if you go to Apotheker, you find perhaps betadine. It's a polymer that contains some I3- anions, and with contact with your skin, it produces the iodine, which simply works as a disinfection agent. Yes, so I want to mention some methods and terms we normally use. Perhaps not all of them, you know all of them. And one that perhaps all of you know is a template. The template supports the formation of a special shape of a structure of a product. We really often use this template approach. And if we have a template that looks this way and we have two molecules that perhaps looks this way, you just understand that it will perhaps make this arrangement. If you don't have a template, it looks perhaps this way. In real, we just have then this chain molecule here, which supports the formation of an aluminum cobalt phosphate entity. It's really a strange arrangement, and you will understand it will not survive without a template. This is one term we often use. The second term you all have already known, and it's on the title page. It's crystal engineering, and it means the construction of new crystal using a rational design, which is in the best case based on predictable construction rules. Here, a simple example from other groups. We have a cobalt bromide, which makes these chains in this direction from upper to lower, and these are then connected by bipyridine ligands to produce this two-dimensional layer. So if you just see the formula, you would perhaps even suggest that it would be this structure. This is called crystal engineering, and we have another interesting term which was coined by Lars Klo really early in 2008 in surrounding of some polyiodides. He said, if a molecule has some special lengths or some special topologies, it also influences the polyiodides I can get from this compound. And in this example published by Resnati and Metrangolo in 2010, we see this organic tecton or template, and then we have an I4 2- anion, which really good fits with this with this shape of these molecules, in this case cations. So this is sometimes also called tecton if we connect these organic templates with others. So this is then called dimensional caging. Throughout all our results, I will sometimes simply use these terms. How we produce our products, it's really simple. We have nitrogen-containing organic starting materials. We react them with hydroiodic acid and iodine in different ratios. Then we crystallize our products. We use, for example, higher pressure or temperature to crystallize it. And then we characterize our products firstly with Raman spectroscopy. In the best case, then single crystal structure determination. But in any case, we should have an elemental analysis. And in the case, if we have perhaps even some phase transitions, we should have some thermal analysis. Okay, we just made in the last years a lot of compounds on all these starting materials, succeeded in producing some polyiodide containing compounds. It's much too much for one talk. So I selected groups and molecules I want to show you today. And we should start with the group of D-amino alkane compounds, and we have them in different chain lengths. And yes, let's start with this group. So we just produced a lot of compounds from this class of compounds with different motifs, and analyzing all these structures, we got 3 general types of structures from this class. So the first type is characterized by the situation that you have a hydrogen bonded network, which is a host for a polyiodide. Yes, so just hydrogen bonded organic tectons or the templates that just make a framework, and then you just put some polyiodides inside. So we start with the C5. I always have here on the left side the chain length. You don't need to count it every time, so it's here. And we start with the C5 system. You see that we have hydrogen bonds between the I- and between the I3- with this NH3 plus centers, and then we create this framework. And we have also some anions that are just in gaps or just in holes within this framework. Yes. When we look inside the structure, we see that we have really similar areas. This looks really the same as this, but in detail, it's a little bit different. Yes, you see that this group here and the A, you all see hopefully my this cursor, and you see this NH3 group has a different orientation like in the layer below. So this type of behavior, that we have very similar motifs in a structure, but not exactly the same, is called pseudosymmetry. So that type pseudosymmetry is always problematic in crystal structure determination. And the definition is given by Michael Ruck already in 2000. He states that the term pseudosymmetry means a spatial arrangement that feigns a symmetry without fulfilling it. But most of these effects complicate crystal structure determinations considerably. So what we have to expect, and I want to show you a diffraction pattern now, which really shows you how it looks like in natural life, I call it. So we have a diffraction pattern with really bright and dark spots. These are these intense spots in the diffraction pattern. And we have some smaller and not so intense spots between them. So we zoom it out and we can find out if we have this A/C/ coordinates, or this, then we just only are fixed on the strong reflections, but the true unit cell is defined by these AC vectors, which then takes into account also these weak reflections. If we take into account all these weak reflections, we really have a small deviation from this substructure situation. We only have 2 iodide anions that significantly break the symmetry. And of course, the organic molecules a little bit break the symmetry. The advantage of this true structure is that we always have then ordered structure. So you can as a take-home message is more or less that you just, if you have a really ordered structure without any disorder somehow, you can be really pretty sure that it's a true structure. If you have somehow a disorder, you should be always a little bit suspicious. Okay, the R factors are given throughout the talk, and there's a rule of thumb. This R factor based on this F parameters should be below 5, and the R factor based on the F square should be about below 10. So this is completely in the scale. Okay, we go to the next one. It's a CH. It's a C. I lost my cursor, my spotlight. Okay, we have a CH organic molecule which is connected to a iodide, and then we just obtain this square hydrogen bonded motifs which are connected to each other, and these parts of the structure are then connected to the next chain of these squares. This creates a framework, and in this framework we have channels, and these channels are filled with a polyiodide. You see here. If we look into detail into this polyiodide, we find out, okay, it's constructed of an I minus, and then 3 times the I3 minus, and then it starts again. So this is an interesting new polyiodide, which is fitting with the length of this framework. You see, it starts from here to here, and then you have this sequence again. So the idea is now simply to change the length of this organic molecules to get other polyiodides. And of course we did. We go to C10. When we go to C10, we also get an organic framework, hydrogen bonded by this iodide anions. We see always this square motif, and within this polyiodide, we only have I3 minus anions. So it's simply a simple polymer which is created by this I3 minus. Yes, and they are always located in these channels. This structure is already published, and it made a lot of problems. I want to show you why it makes a lot of problems, and I had a lot of discussions with the reviewers in those times, because the framework that produces this host framework has a centrosymmetric situation. That means that the framework has inversion centers here at these dots, where these red dots and this location where these red dots are. But you directly see that the I3- ions are not fitting with the inversion symmetry. So we have a reduction of the true symmetry. So to the true symmetry, and the true symmetry is P21. And why we believe, or why we are so pretty sure that it's really this low space group, a lower space group. First of all, the diffraction pattern shows some features that only are just in constant with, or just fit with the P21 space group. But the more important point is that all I3- ions have a normal, typical geometry in the lower space group. If you go to the higher space group, you always have a lot of problems. They just are distorted. And also a take-home message for all these cases is, if the structure still has some geometric problems which are unexpected, so it's or you didn't expect it for this molecule, it could be simply a crystallographic problem. Okay, so we just seen C8, we have seen C10. We now go to C12. Just not very surprisingly, we have these well-known wavy layers. In this structure, we still see the squares. We see the connection to the next stack of squares. And we also see, again, some channels, and these channels contain a polyiodide. Here I want to show you something really special. If we just produce such a material, we first of all make a Raman spectrum. And this is a part of the Raman spectrum. And we are really happy when the Raman spectrum is complicated, because all these iodine bands or signals, in the case of Raman signals, just in the range between 0 and 250 centimeter -1. So it is, and you see here the signal for a iodine molecule at about 180, which is simply a little bit shifted to lower numbers. And we see here really a completely complicated spectrum. This always indicates that we have a complicated polyiodide inside. In this case, we have a iodine molecule and 3 I3- anions behind each other, and then it starts again. Okay, so also in this case, we have pseudosymmetry. It is shown that we have some crystallographically independent molecules here within. You see it starts with C1 and N1 and C1 and ends with N4. We have 2 complete organic cations. And when we do a normal crystal structure determination, which all try to, don't irradiate so long, because the next project is waiting, and perhaps we can make it faster. In the field of polyiodides, it's complicated. If you make a normal structure determination, your picture would look like this. It would simply say, we have a lot of reflection. They are just nicely separated. Only here in the 0 level, you see that there could be something problematic. So for our determinations, we always use really long exposure times or very intensive source. And then the diffraction pattern looks this way. And only if you just harvest all this information from also these weak reflections, you really got the true structure and the full image of all of them. Okay, let's sum up. We had 3 compounds with different iodine to cation ratios. And we started with a iodine poor compound and ended up with a iodine rich compound. This is really a crystal engineering approach. So a second type of compounds is found in this system where the polyiodides are a part of the network. This is more naturally, you have this positive NH3 groups. They should have some hydrogen bonds with the polyiodide, and you see these green dots. We found a lot of them. So let's start with C7. In the case of C7, we have a arrangement like in a box. So 2 cations and the 2 I4- anions just form such a box, which is connected to 4 other boxes, and this produces this interesting structure. This is a typical case of this dimensional caging. We have simply this dimension of the I7, and it works in this way. So we go 1 step down, we change to C6, and we also in this case have this simple synthetic protocol. We just have iodine and hydroiodic acid, and in this case we get a 3D network again, but it looks a little bit different. So we have here other arrangement of our squares, but it's also works so good. So we have obviously a range where we can produce some ions. If we want to have other ions like I5, 6, 7 or something, go further. Okay, this was dimensional caging. So let's go further. We just also tried a really short chained tecton in this case. And this is so short that it really doesn't work with I3-, but always in hydroiodic acid, we have a lot of water. And in this case, simply the water molecules are added as part of the tecton. So we just understand, so the cation plus the water as this primary, this tecton, which produces our polyiodide. Also here we got this I3- one-dimensional chains. And the funny thing, or the fun fact, is that it's these chains run along the B direction, and especially from this point here, from this iodine position to this next iodine position, is exactly the lattice constant. So it's sometimes you just see in the unit cell already the structure. Yes. Mm-hmm. A really interesting case we got from the C8 compound. Also here, you just follow my pictures. You have these squares that are connected to each other, and it's again connected to the next chain of squares. But in this case, we really got an interesting case because we had inside I6 2- anion. And when we published it in these years, it was more or less not, nobody knows, it was not published, it was not characterized. And also in this case, we had some discussions with reviewers if it's really a I6 2-, but we should go into detail. We have this really asymmetric I3- with 2.77 angstrom for this first bond and 3.18 for the second. But it's really, yes, it's obviously a I3-, and we have really short secondary halogen bond between these ions. Fortunately, our Raman signals just really supported this asymmetry, and also the the detailed geometry between the ions support our finding that it's really this first and most asymmetric I6 ion, and it's now in the list and also in this list of new polyodides. So let's go up to another type. The next type is simply that we have some cations trapped in an anionic network. And in this anionic network, this is the most rare case. We have here an example that we just created a polymer. This polymer consists of a iodine molecule, an I3- and another I3-. I show it to you. We start here with the iodine molecule, then we go further this I3-, then this perpendicular to this I3-, and then we start again with the iodine, yes? And these polymers are arranged in one layer, and in this layer, just also our templates are arranged. And if you're just a little bit creative, just you could see a caterpillar in this template. And so I just produced also the caterpillar here in the structure. So the caterpillar more or less makes the details of this structure. So summing up, we can just classify all these compounds to all these three types of polyodide structures. So that's the first chapter. I want to go to heterocyclic tectons, and the really simple tecton is the bipyridine. The bipyridine can react with hydroiodic acid and a iodine molecule, or iodine, and we just put in some iodine. And when we do it, we got within several minutes dark red needles, and these dark red needles just are on the surface of the material of the solution, and you can simply just grab it or just harvest it. Yes, and the structure is also really simple. You have a I3- polymer, and it is cross-linked, means you have this I3- perpendicular to this one first, you have a second, and so on. Neighboring chains are then just arranged that there will be created a box, and in this box you have the bipyridinium decadine. So this is, I guess, really a classical case of dimensional caging. So you have a box, and this tecton or this template is within the box. The interesting case is after a few hours and even after 2 days, all these first crystals just disappear, and we got new crystals. And these new crystals anyway contain water and a much more complicated composition. So we look into the structure. The first thing we just recognize is that we have two cations here and here that are connected by two water molecules by hydrogen bonds. These big tectons just give us the chance to give a bigger polyodide. In this case, it's simply a I14 4-. It's constructed by a iodine molecule and two I3- here and I3- here. So we have really this hook-shaped I14 4-. And when we published it, it was also one of these new polyodides we just got. Okay, let's hop to my last topic on polyodides. It's really new. It's just in the last years, I just was interested in some drugs. And if you are interested in drugs, it's a good idea to have drugs that are just freely available. And we just were interested in these methyl xanthines. And you know that caffeine is in your coffee, and theophylline is in the tea, and this theobromine is in chocolate. All of these molecules are just hydrogen bond acceptors and sometimes also donors. They are used in medicine. For example, theophylline was really used in Corona times as a emergency drug. And yes, it's naturally occurring. Using these methyl-xanthines, you can produce also some polyiodide structures. And the first one I want to present is this one. You have hydrogen-bonded theophylinium compounds. And in this theophylinium compound, you have a dimer, which means that two cations are connected by hydrogen bonds to form this dimer. You can also discuss this structure in the other way. You can simply count theophylinium cations to form a ring. This is number 1, number 2, 3, 4, 5, 6. So we have this ring here also. In result, we get a layered structure. And this layered wavy structure is really useful to structurize polyiodides. You have one layer and you have a second layer, this hydrogen bonded layer. And then between them, you can simply put in some polyiodides. And in this case, we just found this I10 to minus anion, and this I10 to minus ion is just in the literature the second, and in our case, really good characterized polyiodide. So we just have also here not only this template effect of one molecule, we have this template effect of a whole layer. So perhaps this is the idea, this more interesting idea. Okay, so but sometimes we just have some more crystal structures if we just work on it. And also, like in this case, we just have a compound which contains some additional water. And then we have, again, this hydrogen bonded dimers of the cations. Then we have a water molecule. And the interesting case here is that we again find such a I6 2 minus. It's sometimes strange. So until the 2000, nobody just published I6 2 minus, and then just not we alone. Many other people just published since then some of this I6 2 minus. And in this case, it's really a normal I6 2 minus. The I3 2 minus are not so distorted, and the distance between them is in a normal range. So it's not this record structure, but it's interesting to have it in this system. Okay, let's hop from the theophylinium to the caffeinium. If we react caffeine with hydrochloric acid and iodine, the first compound we get is composed of neutral caffeine, a protonated caffeinium, and the counter anion. So this is not so interesting at that point, but if we go to the packing, we just see several things. First of all, we see these two molecules connected by a hydrogen bond, and neighboring molecules are parallel to them or just perpendicular to them. And in result, we get again some channels, and in these channels, we still have this I3 minus anions. So yes, this is really this new structure. Then we just had really good crystals of a really known structure. Yes, okay. Animation comes later. The really known structure is the caffeinium triodide, or triodide, or this caffeinium I3. It is known, and it has been published by others decades ago. And you see the framework, the hydrogen bonded framework, which is constructed by the caffeinium cations, and I showed it here as a wireframe diagram. Within this wireframe, diagram, you see also these black dots. They represent inversion centers. That means this hydrogen bonded framework of caffeinium cations have inversion centers. But if you look into this I3- anions and their arrangement to each others, you see it doesn't fit with the inversion center. So it's not a surprise that we have a non-central symmetric space group. What we did then was we just cooled it down and were surprised that we just got a single crystal to single crystal transformation. And at the end, we just have, again, the same framework. So you see here the inversion centers of the framework. But now the I3- ions are just perfectly within the symmetry. Yes, perhaps we go to this inversion center and you see this I3- here and here downstairs. Yes, here and here. So perfect. So this was also interesting for me, and I just make really, I just want to find out how it works. And I made some diffraction experiments in between. And if we just start here, we make a diffraction pattern or the diffraction image from the starting crystal at room temperature. And I was interested if some reflections just disappear or what happens to the reflections. And what we then obtained was the interesting case that we can follow the phase transition optically. So in this middle image, you see that some reflections stay the same. They're just stable. Yes, they are mostly affected by the framework that doesn't change. But some reflections are simply really heavily involved in the phase transition, this reorganization of the I3- within the channels. And at the end, you see that reflections even simply disappear and we come to this higher symmetric polyodide structure. It's, for my work lifetime, it's the first time I ever see such a really this looking into the crystal and see the phase, really see the phase transition. I was really happy about this. And it's also still not published. Okay, last chapter, in iodine-inclusion compounds. I want to make it here short and brief. We sometimes have the situation that we have some iodine molecules within some gaps, and sometimes it's yes, we just thought about to do it, and sometimes it's by chance. The first thing is that we wanted to do it. This is a short chain tecton, and it's constructs with 4 of these cations and 6 I- constructs a cube, and within this cube we have some disordered iodine molecules. Yes, and the interesting point is that you can pump it up, you can pump it out of the crystal and then give iodine back, and it accepts it again. So it's reversible. So this was really an interesting case. Sometimes it's unexpectable. Unexpectable in this case is this structure. We have this dimethyl phosphoryl aminium cation with some I- that make a bag or just a box for iodine molecules. We can count it together. Yes, we have 1 phosphorus here, 1 phosphorus here, 1 phosphorus here, and 1 phosphorus here on the top, and we have then the 3 phosphorus on the bottom, and then just around this I- that just connect all of them. And within we have then some iodine molecules. Another case that we recently just found was again in the theophylline system. Also here we have these dimers these hydrogen bonded dimers, and we were really surprised that this hydrogen bonded neutral dimers accept a iodine molecule. So, and the interaction energies between the nitrogen and the iodine are just in the range of this strong hydrogen bonds. So halogen bonds are in this system more or less at the same quality as so hydrogen and halogen bonds have the same quality, and it was Rina Konovalova. Yes. So last point, where to go further. At the beginning, I've shown you that we have in the polyiodide system more or less all the new or all the gaps are filled, and it's really complicated to do new research. And also in the bromine system, there is a lot of work done. But what about mixed polyhalogenides? This is our new topic, and one result I want to show you, one new structure is also in the caffeinium system. We have, if you we look on the right side, we see that the caffeinium cations are just arranged in such a zigzag chain, and there's the next chain, and between these chains we have some counter anions, and these counter anions are just composed of a bromine, iodine, and a chloride, chlorine. This is, to our point of view, the first mixed with 3 of them, which is really not disordered. Before, all the structures that are in the database, and it's only a handful of them, is disordered. But this, in our case, it's not disordered. Why it is important to have it not disordered? We anyway need this bond length to estimate some bonding properties, perhaps to do some calculations, and to fit all our results also with the Raman spectrum. And in this case, we just have really this interesting Raman spectrum where we can identify all these bands, and this is an ongoing project with Mike Wischosek, that we just want to create more of this compounds and to use perhaps even higher, bigger and longer polyiodides, polyhalogenides in this type of mixed polyhalogenides. So I just talked about 40 minutes. I should at the end give some credits to some people and funding organizations. My present team is small. I have a PhD student and a master student, Mike Wischosek and Annalena Behrens. On the slides, you always see some papers with former co-workers. I have to thank the DAAD for some exchange money with Serbia this year, and I have to thank the DFG for funding of our nice diffractometer, and I have to thank Jürgen Graf from ImQuartech, who sometimes helps to measure something if we don't have the possibility here. He has also nice machines. And last but not least, I thank Irina Konovalova for helping with this quantum chemical discussions and also with the structures. So, and I want to thank you all for your attention to my talk.
Thank you very much for your lecture. Nice presentation. So, dear colleagues, maybe you have questions. Our lecture. Okay, I have several. First of all, I would like to ask about stability of your compounds. Such frameworks based on organic compounds and iodides?
Okay, in the case of, okay, I can do it in two ways. If you have polyiodides, the polyiodide don't eat my tectons normally. If we have these mixed polyhalogenides and you just add ICl to your samples, it more or less eats the templates or the organic molecules. Means that there is a decomposition reaction. The stability concerning loss of iodine or loss of ICl or something, it depends if it's strongly involved into the structure, if you have really this polyiodide fixed really hard into the crystal structure, you can put it on the desk for several days and it will not decompose. But if it's simply this, especially these inclusion compounds, if you have a really loose connection of the included iodine molecules, you can't keep it out of the atmosphere, which contains a lot of iodine or ICl.
Okay, and how stability influence on applications of your compounds, real applications?
Yes, it's interesting. Yes, it's this interesting point, you know, about this Kretzel cells. And yes, you have the problem that it reacts with moisture, with oxygen, and so on. But also papers exist concerning this Kretzel cell. Yes, we talk about this DSSC solar cells, that this addition of some amines just stabilize it. And we just believe that especially our D-amines just stabilize it a little bit against this, redox chemistry. And you should, yes, it should be sealed. It should be closed. All these batteries, like lithium accumulators, it's always it's all the same.
It's a lithium, yeah, you're right. Okay. And you know, now we have a special grant in the field of metal organic frameworks. And in my opinion, your compounds and metal organic frameworks are very similar, and there are some analogies between these types of compounds. And MOF is a very popular now object for investigation. What concerns your compounds? How popular study of iodide organic frameworks in the scientific world, I would like to say?
Okay, so I didn't mention it. It's at least one Chinese group is working on this, but I think there are some others that simply include some iodine also in MOF compounds. Yes, they just and they're just in crystal growth and design. There's a paper, and I just remember, and yes, there is work to done, but I don't want to be in this. You know, we have here a MOF person in Düsseldorf, and it's not a good idea to take fishes out of his lake. So yes, you can do it. It's a good idea, yes, and some groups are just interested in it. And perhaps one point I never mentioned in this regard, they always have a ion conductivity, all these compounds. And if you have a chain type, I've shown several of these channel structures, which are filled with polyiodide. They always have an anisotropic conductivity. We roughly checked it, so I don't see an application by now, but it's simply a physical property of these compounds.
Okay. And concerning crystal engineering, you said that crystal engineering is some rules to construct crystals, predictable rules. Can you please provide some examples of these rules to construct crystals by crystal engineering?
Okay. this rule.
Which kind
So
of
if you
rule?
just
It's
okay, if you just want to,
yeah.
if you just want to have a special type of structure. In my case, I was always interested in these polymers and is in this long stretched polyodides that are just new ones. So it's a good idea to have some stick-shaped templates. Other people, one former researcher from Cologne, Professor Tebbe, just used some crown as complexes, big ones, to construct some polyodides that have a complex 3D structure, like a onion type. So the crystal engineering in our field is simply that we just try to combine linear templates to get linear polyodides. If you need something else, you should use other templates. This is more or less this rule in our regard.
Mm-hmm.
And crystal engineering, as I showed with this example from other group, is perhaps more this MOF type idea. Just I have these linkers, and these linkers with a special size produce me this framework. With this hydrogen bonded frameworks we used, it's not so simple to structurize it. You have seen at least one example, it was unexpected that we got something interesting in this. So I guess the probability, if people say I do 90%, I can do crystal engineering, I say it's not true.
Uh-huh. So thank you, dear colleagues. Maybe other question? Yeah, Svetlana, please.
Svetlana.
First of all, I'm very thankful for you for the nice lecture, and I have maybe a more practical question. These crystals must possess a very high level of absorption. Can these crystals be measured at the room temperature, or the use of low temperature is very important?
Yes, this technical question is most important for us. When I started this topic 20 years ago, I was really disappointed because I didn't get really good results. But when we bought our Excalibur diffractometer with the cooling device, I was able to measure the crystals all under liquid nitrogen as low as possible, first of all. And secondly, equipped with this machine, I have a really nice microscope that allows me to determine all the crystal phases. So for all these structures, you have seen the R factors are not so bad. All these crystal structures, this polyodide, you just need all the crystal phases. So it's a high. So we try to get always high quality crystals with at best case 6 or 10 phases. We just index and make them this analytical absorption correction. Svetlana Valentinovna, you were completely right. If you have really something, not so good crystals, it will not work at all.
Thank you very much.
Thank you. Other questions?
Another one? No.
Oh, one. Yes.
Okay.
Okay. Yes. Thank you very much again for your nice presentation. We are from Institute for Single Crystals, and any crystal structure, crystal architecture, crystal engineering, very interesting for us. And this topic was also interesting, and I hope for our future collaboration in this field between Institute for Single Crystals, and Düsseldorf University.
Yes, thanks a lot for invitation again.
So we finish our seminar, and thanks again. See you later. Bye.
Bye.